Okay, so welcome back again. We are going to talk about the next session, session 11.4, particularly the first session of 11.4, that is a direct comparison test. And the tax here or the technique here that we are going to apply in testing convergence for our series is if we consider the arbitrary sequence, an arbitrary series, we want to compare it with another series that we are familiar with, that we know to either converge or diverge. And then based on that comparison, we'll make a conclusion if our arbitrary series also converges or diverges. So the best thing to do, I think, is to start with an example. Let's consider the series given by the sum from 1 to infinity of 1 over 2 raised to the power n plus 1. Well, this series, if it doesn't look familiar to you, at least this one does. The above series, resembles so let me just say the geometric series, because we know the series to be geometric, 1 over 2 raised to the power n. Well, we know about this series. This series is a geometric series we've seen before. It has it's a geometric series that we have seen before, and it's very similar to the series that we said we considered above, the arbitrary series that we have above over here. The series below is a geometric series that we are familiar with. The geometric series is familiar, so it has a first term 1 over 2 and a common ratio also 1 over 2, as we've come to know. So the geometric series, the geometric series 1 over 2 raised to the power n converges since you can just use the formula s. You can find x using the formula, the first term, which is a, over 1 minus the common ratio r. So you have 1 over 2 over 1 minus 1 over 2. And that's just 1 over 2 over 1 over 2, right? So that's just 1. It actually converges because whenever you have a geometric series and your r, the absolute value of your your r is less than 1. It's between 0 and 1, then you are converging. Okay. So what else can we say? Well, that is what we know about the geometric series. It is easy. So let's say it is easy to see that 1 over 2 raised to the power n plus 1 is strictly less than 1 over 2 raised to the power n for all n greater than or equal to 1. Well, this is easy to see. So you are considering the sequence that gives the series, the arbitrary series that we considered in the beginning, and the sequence that gives the geometric series, which we claim to converge. Remember, if you have to show that the geometric series converge, then all that you have to do is to determine R and say that R satisfy the condition for a geometric series to converge. And I hope you remember that condition. You don't have to go through this calculation. You do not. You might not have the time. Okay, so now this is easy to see that this inequality is true. Hence, Sn is less than, so the Sn over here is less than the xn over here for all n greater than or equal to 1. Let's find a way to characterize this to partial sums. So let's call this partial sum, maybe. Let's call this n times, and let's call this n plus. So the sum of the first n terms of this series is less than the sum of the first n terms of this series. So xn times is less than xn plus. So remember that the convergence or the sum of a series, whether a series converges or diverges, depends on the sequence of partial sums. And here we just show that this particular series converges. So let me just state that since Sn plus converges, we have that Sn times also converges. So there you have it. So Sn plus converges, then Xn times will also converge. So that is the whole thing about this direct comparison test. That is the case of the conversion. Well, let's write out the formal definition for direct comparison test. And then we'll go ahead to solve more examples with the direct comparison test. Has two statements, one about convergence and one about divergence. So you consider two series. So suppose you have these two series. A series with positive terms. Remember, everything depends on the sequence of partial sums. So your series must not be one that alternates between negative and positive terms. It might be totally positive. It must be all positive. All your terms must be positive. So the first statement is the one that we just illustrated with our example above. It says that if sigma Bn is convergent and you have that An is less than or equal to Bn for all n, then An must converge as well. The second statement is about divergence. And with your intuition up at this point, I believe you should know how it should go. So how about you try to kind of guess what it's going to be? Write it down. Pause your video, write it down, and see if you get something similar. So if sigma Bn is divergent and An this time is greater than Bn for all n, then sigma An must also diverge. There you have it. Well, let's say let's take some like cases where it does not apply. So cases where the direct comparison test does not apply. That's a big mistake. That's where the direct comparison test does not apply. And does it not apply? Well, if I consider two series, sigma An and sigma Bn, where sigma Bn is convergent and An is greater than Bn, then the DCT or direct comparison test offers no conclusion about the convergence of sigma an. Of sigma an. Okay. And the second one is um if I consider two series again, sigma an and sigma bn, where sigma bn is divergent and an is less than or equal to bn for all n, then again then you have the same statement. So we can say nothing about the convergence or divergence of an in that case as well. So as promised, let's look at an example. And in that example, you are supposed to determine the convergence or divergence. So determine convergence or divergence, of this series of n equals 1 to infinity of 5 over 2n squared plus 4n plus 3. Okay. Well, you ask yourself that what series do I know that resembles this one? And by the way, after this one, I'm going to write out a note that the series is so whenever you have to determine, use the direct comparison test, you have to have two series at hand. The one which will be giving you to test for convergence and one which you already have in mind. That is one which you are familiar with. Whenever you have to find another series that resemble the one that you are given. So right now we've been given this series over here in this example, and we have to determine using the direct comparison test if it is divergent or convergent. What you have to do is to look out for either a p-series or a geometric series. Remember that you can tell based on the value of p if a p-series is convergent or divergent. And you can tell based on the value of r if your geometric series is divergent or convergent. So the first task is to look for one of these two series, a p-series or a geometric series that resemble the one that you have been given. Well, what you can do in a case like this that you've been given a rational series is take the highest power, the term with the highest power of n in the numerator, and take the term with the highest power of n in the denominator and use it to construct your series. So here you say maybe consider 5, the series from 1 to infinity of 5 over 2n squared, the highest power in the numerator over the highest power of the denominator. Well, that is going to give you this series. So we'll have 5 over 2. Remember, we wrote this out when we were talking about the properties of series. So 1 over n squared. Is this a geometric series or a p-series? So you can answer that. Is this a geometric series or a p-series? This is a P series. So since sigma to infinity, this is a P series. And what is the P value? With P equals 2. Remember, a P series converges as long as you have P to be greater than 1. Comma, you have that 5 over 2. The sum from 1 to infinity of 1 over n squared converges. Well, now you found a familiar series and you know if it converges or not. The next thing that you want to do is to look for the relationship between these two sequences. The one you were given and the one you constructed on your own. So you say, consider 5 over 2n squared plus 4n plus 3 and 5 over 2n squared. And at this point, it should be easy to determine which of this is the greater one and which of this is the lesser one. So I think it is obvious. If it is not obvious, I'm sorry. It is obvious that if you don't find it obvious, you find it obvious later. I mean, the one with the bigger denominator, they have the same numerator. So the one with the bigger denominator is definitely going to be the smaller one. So 5 over 2n squared plus 4n plus 3 is strictly less than 5 over 2n squared for all n greater than or equal to 1. Hence, by the DCT, we have that the arbitrary series that we got is convergent. Okay, good. So like I said, whenever you are doing this, you have to look out for your series. So you have to either construct a P series or a geometric series. Let us look at the second example in here. So in example 2, we have to do the same thing this time. So we want to test the series for convergence or divergence. Okay. So what are we going to do? The first step is to construct that familiar series, either um, a geometric series or a P series. So we have to test for convergence or divergence. So what I want to do is to consider this series. It's a series that we are familiar with. So the more examples that you solve, the more like these examples, this portion of the response becomes easier. This is actually the harmonic series, and we learned that it actually diverges. Diverges. And then you can consider, then you look at the relationship between the sequence that you were given and the sequence of the series that you constructed. Which one is greater? Which one is smaller? Well, they have the same denominator, so everything is determined by the numerator. A natural log of k for k greater than or equal to, actually for k greater than or equal to 1. Um, so natural log of 1 is 0, that is less than 1. But if, let's say, you are now looking at, as you take more larger and larger k, you find out that natural log of k becomes greater and greater than 1. So any number after e, you have that this is actually greater than or equal to. So as a matter of fact, let's make it strictly greater than e. For k strictly greater than e, you find out that the natural log of k is strictly greater than 1. So you have that this one is greater than this one. So this is greater than this. And the series for 1 over k is the harmonic series, which diverges. So that is exactly the second statement for the DCT, the direct comparison theorem, a comparison test. And it says that this series diverges. So hence, let's pick up an example, one of the exercises at the back of the book, and see if, and look at how we solve that one as well. Okay. So this is an interesting question to get. It says that which of the following inequalities can be used to show that the sum from 1 to infinity of n over n squared plus 1 diverges. So we already told you that this one diverges. This series diverges. But now we are giving you some sequences, some series, and some inequalities, and we are asking that if we are to show that the series diverge, then which of these inequalities will be helpful? So the first one is that n over n squared plus 1 is greater than or equal to 1 over n squared plus 1. That is one. The second one is n over n squared plus 1 n is less than or equal to 1 over n. The third is that n over n squared plus 1 is greater than or equal to 1 over 2n. Well, whenever you get any of these inequalities, remember that you want to take the other side of that. For example, let's consider A. So let's say solution, consider A. No, let's start from C. Consider C. Well, C says that n squared over, no. So n over n squared plus n is less than or equal to 1. We just met this series, which corresponds to this sequence, which is the harmonic series. So since this series diverges, if you are going to make a statement that this particular series also diverges, the one I'm drawing in the box right now, if you want to say it also diverges, then it has to be greater than the series, it has to be greater than 1 over n. But this time it's actually less than 1 over n. So this is one of the cases where the DCT does not apply. You have something that diverges. Your familiar series is one that diverges. So if you want to make a conclusion about some arbitrary series, then, or you want to say that that series also diverges, then that series or the sequence of that series must be greater than the sequence of 1 over n, a sequence 1 over n. But this one is a less than or equal to, so it does not apply. So you say that DCT does not apply. Then let's consider B. B says that n over n squared plus 1 is greater than or equal to 1 over 2n. So this is why you have to solve more examples, because you have to train yourself to see the similarities. What is really the difference between 1 over n and 1 over 2n? When we talked about the laws of series, the laws of like convergent series, we said that if 1 over n diverges, the series for 1 over n diverges, then if we multiply that series by a scalar, this time in this example, you see that the series will like be multiplied by 1 over 2. So the series, what I'm saying is that the series that corresponds to 1 over 2n will be given by 1 over 2, the sum of 1 over n. And we already know this one diverges. So the same statement as we made for C also corresponds to B. If something diverges, if you have a familiar series that diverges, in order to make a conclusion about something, some arbitrary series, the sequence of that series must be greater than your familiar series, your familiar sequence. Okay. So again, DCT does not apply. Okay. So now, how about A? We want to make a statement that this diverges. And then A is saying, so A says that n over n squared plus 1 is greater than or equal to 1 over n squared. Okay. Sorry, 1 over n squared plus 1. 1 over n squared plus 1. Okay, I think I'm just maybe a little bit. We wanted to say, I made a mistake with the B. So let's clean with a B, about a B, and then come back to it again. I only looked at the series, but never looked at the inequality. Sorry about that. So if we consider A, already A, if instead of considering this, you see that if A, you have n over n squared plus 1 greater than or equal to n squared plus 1. Well, n squared, 1 over n squared plus 1 is very similar to 1 over n, is very similar to 1 over n squared plus 1. It's very similar to 1 over n squared, sorry. Very similar to 1 over n squared. So, in other words, like you could have rather considered n over n squared plus 1 greater than or equal to 1 over n squared. You could have considered that instead. And this will not be any helpful because the series for 1 over n squared plus 1 is the p series that we just saw in the previous example. It happens to be convergent. If your familiar p series or geometric series is convergent and you want to make a statement about some arbitrary series, then the sequence of that series, in this case n over n squared plus 1, must be smaller than the sequence of your familiar series. But here is greater than. Well, let's go back to B. The B is what I was saying that I made a mistake because this series happens to diverge because it's just a scalar. Is when you consider the series, it's just going to be a scalar multiple 1 over 2 of your harmonic series. This is a harmonic series and it diverges. And we have that the sequence for the series that we are considering happen to be greater than 1 over 2n. So that is the second statement for your DCT. It says that hence the series this one diverges as well. Okay, so countless more questions that you could solve to try your hand. I'm not going to solve them here, but I hope you ask me some questions come Monday morning. Thank you. I'm stopping the recording now. The next recording is going to be on the limit comparison test.